Okay, so first let me continue our previous discussions, and feel free to interrupt me if you can. Okay, so the reason I really picked the J2 plasticity is because it's really the simplest plasticity model that we can think of, and from that we can use the machine learning to tackle model that are way more complex. Okay, so the first thing first is that the plasticity model require a measure, and that measure is simply called Mises stress, or as the name suggests, J2. Okay, so if you remember what we talked about, J2 is a scalar, and that gives us a sense of how much shear stress the material is experiencing, and that J2 have a form is actually equals to 1/2 of the scalar product of the directoric stress. Okay, so I hope that you still remember that. And what is the directoric stress? The directoric stress is simply the total stress minus the part that are not directoric stress, and the part that are not directoric stress is actually the mean pressure. So P is actually equals to 1/3 of the chase of the stress. Okay, I hope you remember that. And the directoric stress is actually equals to the Cauchy stress minus the mean pressure times the identity tensor. Okay. Now, S double dot S actually referring to simply have the components times each other, sigma 1 1, sorry, S11 times S11 plus S12 times S12 plus S13 times S13 all the way to sigma S33. And in the Einstein notations, is actually written as Sij, Sij. Okay, so as you can see, the I index is repeated. The J index is also repeated. As a result, when you see a notation like that, then the result of that operation would lead to a scalar. Okay. On the other hand, if I actually write, let me give another example. If I write that Cij times djk, okay, so that on the other hand will give us a matrix, okay, and that is simply equals to equivalent to C dot D. Okay, C is a matrix, D is a matrix, and then it leads to a matrix because J, the index J is shared, indicating I'm having a dot product. Okay, you see what I mean? On the other hand, if I actually write Cij dkl, okay, this is also a product, but this would actually lead to a mathematical quality that have 4 different orientations, and hence it will lead to a 4th order tensor. Okay, so the number of non-repeated index actually tell you the dimensions of the physical quality. Okay, so if nothing is repeat, then the number of phi index, this is why it's called phi index, equals to the physical quality dimensions. If all the index are repeat, like what you see here, then what we get is a scalar. Okay, now to write U surface, we always need the ingredient that a scalar. For whatever reason, it's just easier to use a scalar as a criteria. And hence, J2 is used as the simplest criteria to give us a sense of how much shear the material can undertaking before the material yield. Okay, so far so good. Just recap what we talked about in the previous lecture. Now, the meso stress, we can also sometimes we would like to write the stress as a matrix norm. This is also another way to write the J2. And this would actually lead to the square root of 2 times J2. So what is this? So whatever you see here, this is actually a tensor norm, okay? Or you can think about it, this is actually a matrix norm. Okay, so far so good. What is a norm? A norm is actually a way to measure the length on a very fat surface or fat entity. It cannot use to measure the distance for anything that a curve, but for a fat surface, fat plane, or straight line, you can use the norm as a measure of the distance, okay? Or it gives you a sense of magnitude on a very fat, for a vector or actually a tensor. Now, in the literature, you would also see something called misstress. Mises stand for war Mises. If you know a little bit of German, if you know a little bit of German, which I don't, war Mises, the one part is actually indicate the kind of royal family or actually noble caste is from, and then the real name is Mises. So Mises stress is coming from the war Mises, and then what it equals to is simply the square root of 3 divided by 2 times the matrix norm of S, which is actually equal to square root of 3 times J2. Okay, if we remember what we talked about in the last lecture, this is actually called the distortions factor. Okay, this is related to the distortion effect we see when we actually project the von Mises stress from the principal stress space onto the pi plane. Now, let's consider a case where we actually have a uniaxial tensile test. So imagine that I have that cylinder, and then I apply the normal stress tensile test, and the two ends, they have to be in the same magnitude if the area is the same. Then what we actually have is that the stress tensor is actually equal to sigma 0, 0, 0, 0, 0, 0, 0, 0. Okay, do we agree? Now, this sigma and this sigma are actually two very different things. This sigma, with you see the underlined symbol, this is actually a Cauchy stress tensor. Okay, and this sigma is just a component of the stress that you prescribe in the experiment. Okay. When you measure something, you don't really measure a tensor. You get a scalar, but you need to know where it fit into the tensor 3x3 block. Okay. So here, why is it here? Can the sigma put into the middle part or the bottom? Can it put into the off-diagonal matrix? Can you put it into any off-diagonal component? You can if you actually move your orientations, but then but you would also still have a diagonal part. It's not a smart choice. But in general, you can put in here, you can put in here, you can put in here. The reason that you put into sigma 1 is just for convenience. Now let me ask another question. What is the principal stress of this system? What is sigma 1? What is major principal stress? Oh, okay, you answer. You have a very careful question. You're careful than me. Depends on which part is positive, right? Okay, absolutely right. Okay, here, if I assume tension is positive, sigma 1 equal to sigma 2 equal to 0, and sigma 3 also equal to 0. Okay, so why is that? Okay, because what is the eigenvalue of this thing? Okay, it has 3 eigenvalues, 2 of them are 0, and then 1 of them is sigma. Okay, why do I know its eigenvalues? Why do I know the eigenvalues without calculating anything? Because this is 0, this is 0, I'm already in the principal direction. So whatever you have is already the principal directions. Now, okay, so now I see this from the experimental part of expressing the stress in the total Cauchy stress tensor. Now, let me repeat what I'm saying and then try to compute the dirichletic stress. Okay, what is the dirichletic stress? The dirichletic stress is the total stress minus the volumetric part. Okay, Pi actually is a normal stress that are applied evenly everywhere on the surface, like a balloon. If a circular balloon becomes smaller and is actually subject to isotropic stress, and isotropic stress actually have the can be expressed with a scalar times identity matrix. Okay, so let me ask a similar questions. What is the eigenvalue of this part of the matrix? Yeah, PPP. Okay, major, intermediate, minor principal stress. Okay, goes to P. This is actually why it's called mean stress, and it's actually why it's related to the volume, because I'm squeezing cubic in every direction with the same amount of force. Okay, does that make sense? So I make the object smaller without changing the ratio of the loading, so it just becomes smaller or bigger. Okay, so either I'm putting it in the same amount of force or compressing it with the same amount of force. Okay, and they are all on the same side because there's identity matrix times it. Now, go back to this. What is the S? That would be actually simply equals to 2 divided by 3 sigma minus sigma divided by 3 minus sigma divided by 3, 0, 0, 0, 0, 0, 0. Can you all see that? Okay, why? Because I substitute this there, and what is P? P is actually equals to the average of the diagonal stress, right? So in this case, these two diagonal term is 0, so that would be just 1 divided by 3 sigma, right? Okay, so then this is what I get. Now I'm going to compute the stress, the matrix norm, but I only have a diagonal term. So if I actually doing this, then I have 2 divided by 3 squared equals to 4 divided by 9 plus 1 divided by 3 squared, which is actually equal to 1 divided by 9 plus 1 divided by 9 times the stress. And this equal to 2 divided by 3 sigma. Okay, so what actually happened is that what actually happened is that the meso stress that originally used to determine the yield surface is actually equals to the prescribed stress in a uniaxial tensile test. Okay, so this is actually make it very convenient, because if I have a uniaxial tensile test, I just loading the material all the way until I start to see the plastic deformations, and then I put this measurement into Excel file or into a record. And then I can actually using this to compute the J2, and hence I can detect the onset of the plastic deformations by using a very simple device, the uniaxial tensile test. Okay, I don't even need to directly shear the material, which is actually harder. Do you know why it's harder? If I want to shear the material, let's say this, I actually need to mount the material in both ways, and then I need to apply the shear. Mechanically, it's harder. You see it in soil mechanics, but then it's also more sensitive. For the metal, because the metal, you can apply the tensile test. This is actually a very cheap test to consider. Let me just write down the name. This is actually a uniaxial tensile test. Okay, so far so good. This is Von Mises. And let's see. Okay, and then okay, so now we actually define the Von Mises problem. Then the next thing that are actually very important for us is actually to define the plasticity model. Okay, so previously we defined the 1D plasticity model. Here we will expand it to 3D. Okay, so by the way, feel free to stop me anytime. Okay, so plasticity model require us to actually mathematically represent if I have a material that initially elastic and then at some point actually lead to a plastic behavior. How do I actually, what is the math? We need to use the right mathematical ingredient to describe the entire process, and also need to prepare the fact that if the material is unload, I actually recover elastic loading process. This is different than elasticity, because if I have elasticity, there is no path dependent. I loading it, and then if I know, I'll go back in that directions. This is not the case for plasticity. Okay, so what consequently happen is that I loading the material from 0 strength all the way to this pitch strength, and then if I unloading it, the strength won't go back to 0. This part is actually called the plastic strength. Okay. Now a material, either when the material have total stress, to have total strength change. Okay, this is actually the time, the dot is the time derivative. What actually happens is that either the elastic strength are actually increasing, or the plastic strength is actually increasing. Okay, so this is actually the theory of elastoplasticity. Plasticity theory, we actually assuming that if there's a total strength, meaning that there's a change on the length or the shape of the material, they are either elastic or plastic, but not anything else. Okay, does that make sense? So you can have a scenario, multiple scenario. If the material is elastic, then elasticity implying that the total strength change is equal to the elastic strength change, right? Okay. On the other hand, if it's plastic, what does that mean? Okay, this is very important. If it's plastic, it doesn't mean that all the strength are actually, all the strength weight is actually contributed by the plastic. It's actually coming for, it's actually work for this. Okay, you see what I mean? So elastic case is a special case of that strength partitions in which the strength you don't in all the strength that you generate, you don't generate anything that are permanent. Okay, So if you chew a gum and then you remove the loading, or actually you have a rubber that actually very elastic, if you remove all the loading, it go back to the original shape. Okay. On the other hand, if you try to make a sculpture using a clay, and then you mold the material, then you are applying the loading that are plastic, and if you remove all the loading, then the clay become the sculpture you intend to make. It won't go back to the original ball that you made from the clay. So those are the plastic deformations. In real life, for metal, for all the structural components, in particular for the ductile material tend to able to have a considerable amount of plasticity. Okay, so this is actually the first part of the ingredient of the elasticity, that are actually the partitions of the total strain and the elastic strain. Okay, so far so good. And they are actually also tensor, just like the stress. Okay, tensor is actually a concept that are very similar to matrix, but strictly speaking, a tensor could be represented as a matrix, but a matrix doesn't necessarily to use to describe the tensor. Okay, so but for now, you can just think about it as a matrix at the beginning. Now, there's another theory that are coming from that partitions that are very important, and that is the stress change is actually equals to the elasticity tensor times the elastic strain, which is actually also equals to the total strain rate minus the plastic strain rate. Okay, so this is actually coming from applying the first relationship to the last. Okay, now let me put all the underline here so that it's actually okay. So this is another theory that we apply. We assume one more thing to make the model easier, is that we are assuming that the material have a linear elastic behavior. Okay, how do I know it's linear? Okay, if I have something that are non-linear, I cannot describe it with just a linear operations. Okay, I have to add a quadratic term if it's a polynomial, or I would say CE itself probably depends on the string or whatever. Okay, but CE here is a constant, so even though it's a tensor, it's still a constant, so we know that this is a linear relationships. Okay, and one thing that is very important is that we are making an assumption that the stress can only grow by actually changing the elastic part of the string, but not the plastic part. Okay, so this has an important implication in the sense that only the elastic part of the deformation can store energy. Okay, so your elastic store energy is only equals to the elastic part of the strength times the CE times the elastic strength, so divided by 2. So so your stress itself, the change of the stress, is affected by the principle, is affected by the plastic deformations, but then it only accumulate, you only accumulate more stress from changing the elastic part of the string. Okay, does that make sense? Okay, that makes sense, because if you know the material, this thing is already there. So you see what I mean? So even though if I actually go through one cycle, I don't have any loading, the stress go to 0, but then my plastic string is actually permanently going to be there. Okay. Now then there's another thing that are a little bit different, and then I would use a different color. And that is actually called the U surface. And U surface in the J2 plasticity is simply can be written as the norm of the S minus Kuiper, smaller or equal to 0. Okay, so this is called the yield surface or yield functions if you like. Okay, so what is Kuiper? If you remember from the last lecture, we talked about the piping. Okay, sigma 2, sigma 1, sigma 3, and there's a circle, right? Do you remember that? Okay, Kuiper is actually simply the radius of that circle on the piping. Okay, it's a criteria to tell you how much shear the material can experience before the plastic deformation happen. So the higher the Kuiper is, the more the material can actually store elastic energy before the plastic deformation settle. Okay, you see what I mean? The interesting thing is that Kuiper doesn't necessary to be fixed. So when you load the material, sometimes Kuiper is keep changing, okay? And sometimes even the stress, the von Mises yield surface, the circle doesn't actually, not only can it doesn't necessary to retain the same size, the positions of the center can also move, okay? So that can give you a very rich way to describe the different way the deformation is actually occur. And but later here, I would actually consider first the simplest type of the deformation, in which case I'm going to pin this yield surface fixed into the piping, and then that in if Kuiper is constant and independent with the plastic strength rate, then what we have is then we have a perfect plasticity. Okay, so this is the simplest way of plasticity. What it means is that if the material actually can have any type of stress within the circle, but it cannot have the stress outside of that circle. Okay, you see what I mean? Which is definitely different than elasticity. If I have elastic material, I can simply have any stress we have, but here I'm just putting it limit into the circle. Now what will happen if you actually have something that have perfect plasticity? Okay, imagine that I want to put, imagine that I have a table. Okay, and then the limit stress, okay, just imagine that. And then I actually saying that the material here, the tensile part, okay. So if I actually put a television there, okay, so I don't know how to draw a television, maybe just a box. Okay, at the bottom of it, I will have a tensile loading, very similar to what we see in the uniaxial tensile test. I have this sigma just because of the bending moment that are applying to that material, right? Okay, so if I know Kuiper of it is actually, let me make up some number, maybe 10 megapascal, okay? And then this whole thing is actually way more than that, so that the loading, so that the stress here is actually more than 10 megapascal in order to actually sustain the material. So what will happen? Okay, so what will happen if you put it in finite element? First of all, what will happen? Okay, if you put it in finite element, what will happen is that you will find there is no solutions. Okay, do you know why? Because at most you can only generate 10 megapascal of the stress. Okay, so you cannot balance the force because the material cannot react with sufficient force to actually make the material hold in a static manner. Okay, if it's actually, on the other hand, if you solve a dynamic problem, you get able to update, but you will finding that the table actually fall in the finite element simulations. Why? because the difference between the internal force and the external force will be balanced by the initial force. Then you start to generate accelerations of the material. Okay, if you model it, if you have a quasi-static, you will find those solutions. Okay, so unlike the elasticity problem, if you put the infinite element for a plasticity problem, there is a possibility that you would find out that the finite element solver have no solution, and that could be for physical reasons. Okay, so far we talk about these three. And then the other one that I would really like to talk about is actually another criteria that are actually very important and have a very strong geometric relationship to it. And then I will again use a different color. And that is called the flow rule. Okay, the flow rule we talk about in multiple lecture. And this is the plastic strength rate is actually equal to the plastic multiplier that times the stress gradient. Okay, so this gives you the sense of the magnitude of the plastic deformations, the lambda, and it's always a scalar, and the stress gradient give you a sense of the flow directions. Okay, here I would like to say the following. This one, we call it flow directions, okay? But what it gives is actually not necessarily directions like what you see in a vector, go to x and y, but the type of the deformation you get to accumulate the plastic deformations, okay? So for example, let me give example. If the chase of the plastic deformations of the stress gradient is equal to 0, then what do we understand about the plastic flow? What kind of plastic deformation would you get? If chase of the plastic flow is actually equal to 0, of the stress gradient is equal to 0, then what do you get? What kind of deformation would you have? I think, Chairman, do you know the answer? Yeah, you can have all different kind of plastic deformations, but then it will be volume constant. It will be volume. The volume will be constant. Okay, why is the volume constant? Because lambda is a scalar, right? So if the chase of the stress gradient equal to 0, that means the chase of the plastic strength rate is also equal to 0. So if the plastic strength rate, the chase of it is equal to 0, what it means is that sigma dot P11 plus sigma dot 22P plus sigma dot 33P is equal to 0. Okay, why is it volume constant? Because I'm saying that if I actually imagine that I have a cubic, if I squeeze this part by actually having a sigma 11P, I will be compensated by the other two, so that in summary, the volume would not be changed. Okay, you see what I mean? So if I have a x, y, and z, if I have a delta, I'm basically saying that if I have a cubic and then the length is all L, is all L, L, and L, I'm saying that delta x plus delta y plus delta z is equal to 0. Okay, you see what I mean? So if you actually have a box and then if I increase one side and then the other two dimensions change the same size, the volume would be identical. Okay, so that's why. And what is the example of the chase of the sigma of the stress gradient equal to 0 is actually the J2 plasticity. So mathematically, the plastic flow directions is actually the normal directions of the circle. Okay, and then if you're plotting it in piping in the principal stress directions, the yield surface actually for J2 look like this. Okay, and this is actually the principal stress direction where sigma 2 equal to sigma 1 equal to sigma 2 equal to sigma 3. This is the hydrostatic axis. Actually, you will find that if I look at the circle here, all the circle along the hydrostatic axis share the same radius. Okay, so this is actually how it goes. And you can actually also seeing that from the J2 plasticity. Write the I know I can also write the change of the stress as the change of the as the change of the strain. So for J2 plasticity, remember that the yield stress is actually equals to the norm of the S, the matrix norm of the directory stress minus the Kuiper smaller than or equal to 0. Okay, so now I'm taking the stress gradient, and then that stress, because Kuiper here is a constant, then if I take a derivative of a constant, it leads to 0. So the only term I have that are actually related is this term S double dot S, which is actually just the definition of the norm. And then that would be equals to, if I apply the chain rule in calculus, then I will have 1/2 S double dot S minus 1/2, okay, just the chain rule, times the S double dot S, and then the partial derivative of the directory stress with respect to the Cauchy stress times 2. Okay, so if you remember what we talked about in the last lecture, so what we will have is that we will have this directory stress divided by the magnitude of the directory stress, which just gives us only the direction left, okay? Double dot the partial derivative with respect of the directory stress with respect to the total stress, which is simply equals to the directions of the directory stress, double dot the fourth order identity tensor minus 1/3 identity the tensor times the tensor product of the identity tensor. Okay, or I can write it in index form, so that would be actually equals to that would actually be equals to Sij times the Ijkl minus 1/3 of the identity tensor canonical delta equals to Skl minus 1/3 of Siiikl. Okay, and Sii is actually equal to 0. Okay, why is that? Because it's directory stress. It's coming from the Cauchy stress, taking out the mean stress. So if I take out the mean stress, they have to be equal to 0. Okay, because anything that are from the mean is already taken out. Okay, you understand what I mean? So that is actually Sii equal to 0, because by definitions, S is actually equal to the total stress minus 1/3 of the chase of the stress. So anything from the chase is already taken out from the S. So S, the chase, the diagonal term, if you sum the diagonal term of the directory stress, it has to be equal to 0. If they're not, then that means you haven't taken out all the mean stress out, right? Does that make sense? Okay, so this term cancel out because it's equal to 0. So what we end up with is something very simple. The stress gradient, which is actually called gradient because it's actually is a second order tensor that are coming from taking a derivative of a scalar against a second order tensor. So, and then we will have this, which is actually equals to n. Okay, so why do we choose the symbol n? Why do we use the symbol n? N in all the number have a very specific meaning. People, mathematicians like to use the n to indicate directions. Okay, so here, this is actually the flow directions. Again, I did not use the plastic potential, so that the stress gradient is already the directions. And as you can see for J2 plasticity, the volumetric stress doesn't play any role on the plastic deformations. Okay, the volumetric stress is assumed to remain elastic if the material is actually isotropic. So with that respect, finally, we come up with a very simple conclusions. The plastic strength is actually equals to the lambda dot times the n. Okay. And there is one beauty of that is that because n is actually the s divided by the magnitude of s itself measured by the matrix norm. So if I actually want to know how much plastic strength I accumulate, and I take the norm of the plastic strength rate itself, what I will have is that lambda dot times the n, and n itself is actually equals to just the would be equals to the magnitude of the s divided by the magnitude of the s, and that would be equals to lambda dot. So lambda dot actually called a plastic multiplier for that reason. It gives us the magnitude, the sense of the magnitude of the plastic deformation we accumulate, and then the n is focused on the directions. Okay, so we have a separate way to mathematically represent the how much deformation, plastic deformation I have in lambda dot, and the type of the plastic deformation we have for the n vector. Okay, in this case, n is a tensor, but you can think about it in the piping, it become a vector. Okay, so the sense and the magnitude are actually separated, represent, and then when they combine, they give you the plastic strength directions. Okay, so then again, the chase of the epsilon dot p is equal to 0 for the U surface. That only depends on the measure of the strain. Okay, now this is not good for model soil or even for metal in a very high pressure, because if you subject something into a loss of compaction pressure, it always shows some pressure dependence. Okay, but J2 plasticity is the first model to derive, and it's actually work a lot for metal. It doesn't work for soil. Okay, and hence it's worth to talk about it, and it's actually easier to understand. Okay, so far so good. Slide. I know that I can write the plastic string like this. Okay, and I know that I can also. Okay, now the plasticity theory is actually really abstract and really hard to imagine, but really hard to understand. But to make it easier, one way is to think about it in the geometrical term. Okay, so if I have in this case, I would actually have the yield stress that look like this in the principal stress directions. And I would specify what is perfect plasticity here. Again, perfect plasticity simply meaning that Kuiper is actually equal to constant, and like what I said before, doesn't depend on the lambda or the plastic strength change. Now here, then we have one more conditions that we haven't talked about, and that is a necessary ingredient to complete the computer algorithm. and that is called the consistency conditions. Okay, what is consistency conditions? It comes from the fact that f dot has to be equal to 0. The change of the yield functions has to be equal to 0. Okay, so why is that? Why do we need f dot equal to 0? How come f cannot change in some way? Okay, in general f can change, but then on the yielding point, the f itself can evolve, but then the material, when the material is yield, f is all equal to 0. Okay, so if I write a elastoplastic strain wave even in 1D, that would be sufficient. So this part is elastic. Okay, so I lower the way here, and all of a sudden I see the degradations, and then I see some hardening in this particular case. Now, this is one thing that is important, because in this part the material is yield, or the material have plastic yielding, and we say that when the material is yield, if material is yield, then f has to be equal to 0, not smaller than 0, isn't it? Okay, now if I continue loading the material from here to here, that means during that entire cycle, f have to be all equal to 0, right? If suddenly f become greater than 0, then the stress is not admissible, it's not real, okay? Because it's outside of the admissible range. Now, if f suddenly becomes smaller than 0, that also doesn't make sense, because I'm loading the material all the way until it yield, and all of a sudden it becomes elastic again. Okay, so it doesn't make sense unless you have some non-convex yield surface, but in general, we won't consider that. So consistency condition basically is saying that if I write the plasticity model correctly, during the loading cycle, the f would remain 0 for the given stress that I'm loading the material. Okay, does that make sense? Okay, this is called consistency conditions. Now, what is the implication to that is that it will give you a way to write the plastic multiplier as a functions of the strain and the directory stress directions. Okay, to see that, we simply need to write out the yield stress as a time derivative. So F is actually equals to the directory stress minus Kuiper. Sure, and they have to be smaller or equal to 0. Did I write it correctly? Yeah, did I write it correctly? Yes, that's correct. Now I take the time derivative, okay? So take time derivative. So F dot is actually equals to the partial derivative of the stress of the yield function with respect to the stress tensor times the stress tensor. This is actually, again, coming from calculus. Okay, so if the material is consistent, this change is equal to 0. Okay, does that make sense? Okay, if the material, if I continue using it, and then mathematically I write the equation that are actually correct, okay, then this thing has to be equal, then the f dot has to be equal to 0. Now, for perfect plasticity, Kuiper is constant. For perfect plasticity, so if this is actually constant, if something is constant, you take the time derivative of it, then they will lead to 0. So a Q of this term. Okay, so far so good. Now then I have this term left. Okay, and I know that this term is equal to 0. Okay, now it doesn't look like it's useful, but let me go back to the previous. So if I put these two things together, so what I would have is that this one will give me n. Okay, so far so good. And the stress rate will give me C dot plus total elastic strength, so total strength minus the plastic component equal to 0. Okay, so far so good. Now then, with that, then I would actually apply the flow rule that we actually preset there. This is like cooking a chicken or something. I prepare the gravy and now I put the gravy into the potato. Okay, that everything is pre-cooked. I just assemble those components in terms of deviations. So I have that lambda actually times the stress direction equal to 0. Okay, so now there are something. Sorry, it's not C dot, it's CE. Okay, so this is actually the elasticity tensor. Okay, so what is actually so special about this equal to 0? Now I actually have something that actually very good, because I already know what is the plastic strength way that I accumulate if I load the material. Because that would, if I do some algebra, I will put the lambda onto the other side. I'll put the lambda dot onto the other side, and I can actually do some algebraic operations, and I will get n dot double dot c dot double dot epsilon e divided by n dot c e double dot n dot. Okay, I'll have exact expressions. Why do I actually come up with this? What is the trick for me to get this? Or do you know how I get from here to here? How do I get rid of the n from here? So how do I get out from the here? It's like magic, right? Well, actually, I'm just have the first term. So this part apply to this, and this part apply to this, and that's it, right? Okay, so nothing special. Just okay, and then if I write it in the Einstein index form, I'll have NijCijkl. Notice that in that index form, you don't write out the dot. Okay, instead, you use the index to indicating that what kind of product you get. It can be a scalar product, it could be a vector, it could be a tensor, or it can be something completely wrong. Okay, so I write it like this. Now, what I should get is a scalar, so there should be no phi index. What it means is that all the index will appear in pair, okay, and there's nothing left. So I appear twice here, J appear twice here, K applying twice here, and L apply twice here. So what it indicates is that there's a there's a dot product or there's a scalar product that reducing the grade, and then you end up with a scalar coming out from the multiplications. Here you see the same thing. There's 2m here, 2n here, 2o here, and 2p here. Okay. So in general, there's a requirement on the elasticity for the plastic part to make sense, and that is CE has to be positive definite. Okay, why CE need to be positive definite? How come CE cannot have an eigenvalue equal to 0? It's kind of fun, right? Right? Okay, so what happened? If CE actually is not positive definite, you cannot guarantee that this whole thing is actually greater than 0, and you may end up have a ill-defined plastic multiplier. Okay, so in general, when you write a elasticity model, you always assume CE is positive definite, unless you know what you're doing. So for example, if I want to model scheme, then I may have purposely have some potential value or some feature that give me the bifurcation or unstable mode. But in general, I would actually write a stable model so that the Hertzian matrix, in this case linear, so the Hertzian matrix is constant, is always positive definite. Okay, it's just to make sure that the model is stable. Okay, so far so good. Okay, so should we take a little bit of break and then we continue? Do you think it's a good time to give a break? So why don't we have a break? Because it's really hard to pay attention. Listen to me for very long. I think my PhD student told me that. So I would. Why don't we take a 10 minutes break and then we come back? Actually, why don't we take a little bit longer? Why don't we come back at 5:30, so everyone is recharged completely? Okay, so we compute the lambda, but what is the implication of that? Okay, sorry, let me put it back. Okay, so J plasticity is actually one of the simplest plasticity model, and J2 perfect plasticity is probably the easiest algorithm to put it into a computer precisely because of that. I have an analytical form of how many plastic flow I generate, plastic the strength rate I generate, and I already know the type of the plastic directions, which would be on any part of the U surface, would just be the normal part. Okay, so I have an easy time. I know the magnitude, I know everything. I just need to introduce something called a return mapping algorithm or radial return algorithm. And what I want to talk about is to talk about this algorithm. Okay, now the algorithm is needed whether you actually have a machine learning use service or handcraft use service, because you need to actually make a predictions of whether the material is elastic or plastic, and then you need to correct it. Okay, that I divided here to rewrite the stress. So what I actually already have is the strain rate as a function of the elastic strain. Okay, but I don't want that. I want to instead have the stress rate equals as a function of the total strain. Okay, how should I do that? I just need to doing this, and I actually want to save some time. I will just call it X. Okay, just to. So let me first talk about the following scenario. In what we talked about before, we talked about the waveform and everything that are continuous. In a computer, you are not going to actually make a prediction continuously. You're going to actually make a prediction from strength from the previous stress with the previous strength with the previous lambda, okay, and with the previous plastic strength. Okay, those are given. And what else should be given? And then now I actually need to load the material a little bit more, which is the delta epsilon, which is actually equal to the delta, which is actually equal to the epsilon n plus 1 and minor epsilon n. Okay, so in a computer, everything is incremental. So I'm actually giving this, and what do I need to predict? I need to find what is the new stress. I need to find what is the new plastic strength. And if I know that, of course, I know what is the elastic strain. and then I know what is the delta lambda n plus 1. Okay, this is what I want to find. Okay, does that make sense? And then there are already things that I know from the previous lecture. First of all, we already know that lambda dot has to be greater or equal to 0. Okay, why is that? Why is that? It's just the definition of the norm. It cannot be. Okay, in the worst case, it can be equal to 0, but it won't have anything that actually less than 0. Okay, it's like an inner product or a link. Okay, have you actually able to buy have you able to actually find something that can negative 1 centimeter? I guess you can if you actually consider the direction, but if it's purely a magnitude, then you won't actually have that. Okay, now there's another thing that we know, and this is actually appear to be a little bit new, and that is that n double dot sigma ij chi is actually greater than 0. Okay, so I need to define something. What is the chi stress? And then from that, things will make sense. Okay, so what is chi stress? Okay, so this is actually coming from writing in the computer. We actually don't have a continuous strain or continuous stress as a function of time. Instead, we have multiple discrete time steps. So from the previous time step, I have a U surface. Okay, F sigma n Kuiper equal to 0. Okay, now I actually know that in the previous step I'm here, okay, at one of the point, okay, because any point in that surface from here to here is going to have f equal to 0. Now in this case, I'm actually going to have the delta lambda, delta epsilon. Okay. Now at this point, I knowing that the delta epsilon, just like the epsilon dot, would be either equal to the elastic part or the plastic part. But I don't know what is the portion. I don't know how they split. Okay. It could be all plastic. It could be all elastic. Okay. It could be a combination of both. So I don't know. So one of the easiest guess is that I assume everything is elastic. Okay, if I assume everything is elastic, then what I will get is that I will get a tri-stress. Okay, so the tri-stress is simply equals to the previous stress. Is equal to the previous stress, and maybe I will write in this form. Let me take out the index. The tri-stress is simply in the computer is actually equals to the previous step times the elastic strain times the total stress times the total strain. Okay. Now the charge stress is called charge stress because we don't know whether it's correct. Okay, I'm just guessing. I'm making a guess that the whole thing is elastic. Now, and then what actually happened is that I actually need to test the hypothesis that everything is elastic, and if it doesn't work, I need to able to correct it. Now, notice that the charge stress, because I'm moving it from here to here, is always pointing outward. And what is the normal stress? The normal stress is always here. Okay, it's 90 degrees to the tangents of the circle, and that is the Nij. Okay, so on the piping, there's actually one very interesting relationship is that this angle is always less than 90 degrees. And if this is less than 90 degrees, then what happened to the dot product? They would be positive, okay? Because they're not orthogonal to each other. For dot product to reach 0, I actually have to have orthogonal, right? You see what I mean? So this is actually explain why this is positive. So with that, then I would actually start to write a case. I have the following tasks that are actually could be not so difficult. So what I want to do next is that I want to able to write a string increment as a function of the stress total string increment. Okay, do you understand what I'm saying? Because I actually don't want to write it as elastic string because I'm only given the change of it and then I know the total string, and then I want to use my knowledge to do some algebra. Before some time. Okay, so and what we would actually able to get is something called elastoplastic tensor or tangent operator. And sometimes also people just call it tangent. Okay. So in the special case where the material is elastic, the elastoplastic tangent, the operator or elastoplastic tangent tensor is simply equals to the elasticity tensor CE. Now I'm going to use what I have for the J2 plasticity, which is again doesn't have volumetric component. The total strength rate is actually equal to the CE double dot epsilon dot minus epsilon P. Okay? In other words, the plastic strength rate doesn't affect the change of the stress, only the elastic part. Now, I substitute my knowledge for the J2 plasticity. This is actually going to allow me to rewrite the total plastic strength as the change of the magnitude times the directions of the stress. Okay. And that would be actually equal to CE double dot epsilon dot minus lambda dot n. And n is simply the normal directions of the circle in a piping. Okay, so far so good. Now, I actually you see what is my difficulty here is that I need to get rid of this. I need to get rid of this. So everything is a function of the total elastic strain. Okay, so I simply need to provide some substitutions. And the first thing I need to do is that I would, for simplicity, switching it into Einstein index form so I can provide more details. So this is the equations I actually have in the tensor notation. Now I switch to the index form, and that I will use a different color. I will have epsilon ij dot equal to CE ijkl times the epsilon kl minus lambda dot nkl. Okay, so far so good. I'm just rewriting this in, okay, they're identical. Now I'm going to use the results that I'm actually used that on the writing. And what I will have is that I substitute the result here. What I will get is that this is actually equals to Cijkle times epsilon dot kl minus NAB CABCDE epsilon dot CD divided by the x that we have. Okay. Now, do you notice that I use ABCD here? Okay. Why do I do that? Actually, no specific reasons. The notations that you choose are actually irrelevant. You can, if you like, you can use MNIJ, or you can actually use what are the other example? MNST, okay, or you can use XYZ. That anything is good, okay. The only thing that actually matter is that whether they are actually related to the index or not, okay. Sorry, this one I still need to put the NRKL there. Okay, so this I need to actually provide a more detailed derivation here. The first term I will get coming from here is that this apply to here. I will get Cijkl E epsilon dot KL. Okay, so about this term is clear, right? Now then I actually need to consider this term apply to this term. Okay, which is actually equals to 1 divided by x. I just consider it as some kind of magnitude. Again, I'm assuming that C is positive definite. Then I have Cij PQ and PQ and AB CAB KL epsilon dot KL. Okay, so this could be pretty confusing. Okay, do you know why? Because what happened to that KL to that what happened to that KL and then the CD here? Okay, now I want you to pay attention to the two index that I guess reach. One is the PG, another one is the KL. Okay, so KL appear here, and KL also appear here. Okay. Now, in the Einstein notations, you cannot have an index expressed in the same term more happen that occur more than twice. Okay. This is actually because in the dot product you have A dot B, but then you cannot have one index simultaneously have a dot product with two things. Okay, there's an order on the operations. And so when you actually share that, so you, in order to represent the operation correctly, you will have to change the index to indicating that I'm carrying out this operation by sharing these two index with the n, and then I'm sharing these two index with KL between these two terms. But the term of the PG and the KL, they are not having the same operation together simultaneously. So these operations and these operations are actually two separate operations, okay? Which is actually not happen here because I have KL, KL, and also KL here. Okay, so you don't want to have a, so this is also another way to check whether your derivation is correct. If you have, you can either have free index or you can have dummy index, meaning that the index is already repeat, but the index cannot repeat twice in the Einstein notations. Okay. I'm not very sure whether the notation is set up by Einstein, but I'm just using that thing, and then I need to add the E here. Okay. So what is so special about this? Okay. What is special about this is that now I have tangent here. Okay, where is the tangent? This is epsilon KL, this is epsilon KL. So if I actually want to do a little bit of deviations, I can take out the epsilon KL dot here, and I have CEIJKL minus this gigantic term. Okay. Does that make sense? Now, if I actually take out this term, notice that PQ is actually not free index, AB is not free index. However, in the second term, IJKL only appear once, okay, inside this bracket, okay. Now, if I actually combining them together, then this whole thing is actually a CEPIJKL. This is actually called the elastoplastic tensor. or more accurately elastic, elastoplastic tangent or tangent operator or tangent tensor. Or sometimes in the literature they just call a elastoplastic tangent, which is actually also a good name. Okay, why is it a tangent? Why is it a tangent? Okay, it's changing. It's actually is in 1D it collapses into some kind of slope between the total strength and the total stress. Okay, can you see that? In 1D, okay. In multi-dimensions, it gives you a sense of what kind of directions and the magnitude and the slope or the stiffness it will go if I actually want to changing the stress through changing the strength. Okay, you understand what I mean? Okay, so if CEP actually itself, if you compute the eigenvalues, you can also compute the eigenvalue in any even order tensor. If the eigenvalue is very high, it means that the material is really hard to change the stress from changing the strength. Okay, if the eigenvalue is very low, then what it means is that actually it's very easy to actually if the it's actually very you can hard. Sorry, let me correct it. If if the CEP have very high eigenvalue, that means that it is actually you can change the stress easily by actually changing the strength. Okay, you see what I mean? So strength and stress have a mapping relationship, and you can control the stress from changing the strength. Now, if CEP is singular or have zero eigenvalue, then that means that you can actually changing the strength a lot without changing any stress, which lead to the material being unstable. You see what I mean? Can you see that? If I can actually deform the material from here to here, and then I don't even change the stress, then I can basically lost control of the material. I probably don't want it to be put it into a racing car, aircraft, or anything that are very of important consequence. Okay, so this CEP actually could be indicator of the give you a sense of the whether you have exist deformation of the material. Okay, because it's a function directly related to the total strength rate. From the algorithm part, you actually have to compute the CEP in order to be able to put anything into the finite element, because the finite element code doesn't understand what is elastic strength and total strength. You actually get the strength from computing the displacement. And then from the displacement of the node, you apply the B matrix, you get the strength, and then that strength compared to P strength give you the strength rate, and you need to compute the stress. Now this whole thing, if I'm writing it now in tensor notations, which is actually always what I prefer, it's actually CE minus 1 divided by number X CE double dot N and double dot CE. Okay, and this label is actually indicating that N, the N in the left hand side and the N on the right hand side are not share any index at all. Okay, if it's double dot, that means they share both index, and then it become a scalar. Okay, what is N double dot N? I actually talked about it before the break. What is N double dot N? 1. Okay, why is that? Because N by definition is the S divided by the magnitude of S. So S double dot S divided by S double dot S is actually just 1. Okay. Okay, so this in general, you don't want this to be equal to 0 everywhere. Okay, even though you have perfect plasticity. Okay, so here 0 is a tensor. It has also have a different meaning. It's not a scalar. Okay, so far so good. Okay, this is very abstract, but let's consider some special case. Okay, so now consider the fact that I have isotropic linear elastic material okay, so isotropic linear elastic, actually this field work this description have a lot of information. Isotropic meaning that you only need two elastic modulus to describe the entire material. In this case, for convenience, I would use the bulk modulus and shear modulus. Okay. And linear meaning that I can use CE to relate strain rate to stress rate, and CE is not changing when I actually changing the epsilon E. And elastic meaning that the material is not yielding, so these three words have very important meaning. And when I combine these two works, then I would have the following equations. Again, if you actually forget about this, you can find that information from the solidmechanics.org by Professor Alan Barr from Brown University that actually have a very good description of that. So for this course, I will just directly write the result. So this is C E in the isotropic linear elasticity is actually equal to this. So the first term is the bulk modulus. The second term is related to the shear behavior. Okay, if you look at the term, it kind of look like the isotropic. It kind of remind me of the directorial volumetric version, right? Do you see that? Okay, so this one is related to the volumetric stiffness, and this one is actually about the change of the shape. Okay, you can store energy by changing the size of the material and changing the shape of the material. Okay, you store different kind of energy, directoric or shear or volumetric. And for isotropic material, that is a very important characteristic is that if I change the shape, the material just changes shape, it won't change the size. Okay, if I change the size, if the material is isotropic, I won't change the shape, it will just changing the size. Okay. Now, in real life, the material is anisotropic, so if I apply the isotropic compaction there, I may change the shape a little bit. The circle may become an ellipsoidal. Then there would be additional coupling term between the first and the second term, but here we don't have that, okay? And a lot of time, this is a good enough assumptions. Except if you want to model biomaterial, then I never recommend you assume something is isotropic, okay? Or something that have texture like wood. That would be a terrible idea to model the timber as isotropic material, for example. So again, I'm just trying to practice my Einstein notation skill of using this. Okay, so far so good. No, this is actually the linear elasticity tensor. Now, there are actually something that very interesting on that. I don't know whether you learned that from the undergraduate course. So what makes the CE positive definite? Okay, it require okay, if a material is stable, when I say the material is stable, it means that if I actually provide a strain, it guarantees to store more energy. That is called stable, okay? You see what I mean? Then the CIJKL, the elasticity tensor has to fulfill the following behavior in the case the material is isotropic. And that is the bulk modulus has to be greater than 0, and the shear modulus has to be greater than 0. Does that make sense? Okay, so, and that also related to thing is that if I propagate a shear wave or compaxive wave, I actually can propagate a wave from left to right. I don't care about the speed. It could be very fast, it could be very slow, but the wave will be received from the other end, right? Why is that? Because the wave speed is actually related to the compassive wave speed is actually equal to the bulk modulus divided by the density and the square root of k divided by rho. Okay, So if you can propagate a wave, that actually indicating that K is actually positive. Now, what happens if something is incompressible? What would be the compressive wave speed? If it's incompressible. A material that is incompressible means the following thing. No matter how much volumetric stress I'm trying to put in there, if the material is isotropic, I won't get any volumetric strain. Now, how do I achieve that? One way is to make K approaching infinite, right? Okay, if it's actually so stiff that no matter how hard I did, I cannot even, no matter how much stress I put, I cannot even change the strength, then the material become incompressible, right? So what will happen to the wave speed? It would also become infinite, which of course we know is impossible, okay? But water, for example, if you try to have a compressive wave on the water, they should be almost instantly able to propagate from the one side to the other side. Okay, gas on the other hand are compressible. Okay, I mean most of the case. Okay, not going too far away. So in order to guarantee CE is positive definite, you only need the Buck modulus and the shear modulus to be greater than 0. Okay. By the way, what is the corresponding Poisson ratio? Does anybody know? 0.5 is actually when the shear modulus become infinite. But what is the smallest Poisson ratio you can get? Huh? -1? Are you sure? It's negative, you're right. Okay. Actually, I forget. I think it's 1/4, but maybe it could be 1/2. So I have 3 records, so it's embarrassing, but I really forget. But you can check it, okay? By the way, what is the physical meaning of Poisson ratios that are actually negative? Now, Poisson ratio is positive, meaning the following. If I have this, okay, and I deform it, making it longer, okay, then the fact that I make it longer this side, meaning that the other side will become thinner. Okay, so this one is Poisson ratio is actually greater than 0. Okay, if Poisson ratio is negative, what will happen is that I'm loading, I actually making it longer. This side would also become bigger. Okay, it's kind of intuitive, right? Do you know what I'm saying? But sometimes it could happen. Okay. Actually, I have a 9 years old and a 2 years old daughter. So you have one of those toys that you can actually have a mechanical structure that are already stored in this way, and when you're putting it, everything span. So this is one example. If you homogenize the entire effective material, you will get a negative Poisson ratio. Okay, now go back to this. Our goal is to study the plasticity. Why do I care about this? Because I know that if I set the Buck modulus and shear modulus to be greater than 0, I would get a stable response. There would be no problem putting into the final element. But then the next questions I need to check is that I need to check whether is CEP positive definite. Okay, why do I care about this? Okay, I want to know whether it's stable, right? Okay. I think some of you may know the answer already. Okay, so now again, let me actually talk about why the positive definite is important. So first, let me talk about the positive definite. Of the elastic tensor. Okay. Now, if CE is positive definite, that implies the following thing. First of all, if A is a second order tensor, any arbitrary second order tensor, then the quadratic term of this is always greater than 0 if A is actually not a trivial second order tensor. Okay, it cannot be negative. Okay, so on the other hand, if CE have negative Poisson, CE have negative eigenvalue, you can actually get something negative. Okay, why is it important? Because if you add a 1.5 there, that would be exactly the elastic store energy. Okay, and you don't want to create a theory where you store negative energy. Okay, it doesn't make sense. Energy is, you can have no energy or you can have positive energy, you cannot have negative energy, at least not in mechanics. In literature, you can say I have some negative energy, but that has no, but mathematically or in the mechanics world, the energy could be either 0 or positive. Okay, so CE is positive definitely guarantee that you won't actually have those undesirable predictions that actually we know is not physical. And there's also another thing is that if A is actually, if you get this equal to 0, this has to be implied that A is actually guaranteed to be just 0. Okay, why do I actually want this? Why do I actually need this property? Well, so the way to think about it is to think about otherwise. Okay, if you have some deformations, if A is equal to some kind of deformations, and then deformations doesn't store energy, okay, then what will happen? Then that means that you don't have a one-to-one corresponding between the energy and the strength you have. Why is that? So if 2 is violated, then what will happen? Say there's a B, okay, and B double dot C double dot B is actually, let's say, equals to I don't know, equal to X. Okay, I'm just make up some number now, but A double dot C E double dot A is actually equal to 0. Okay, so what happened? What if I actually have A plus B double dot C E? Okay, what will happen? So what will happen? Let's say a double dot A. What would happen? Or maybe B. Okay, you can, what actually happen is that you can start manifest those things that are actually non-unique. So your stress and strength relationships with case to have a unique relationships. Now let's think about another case, the positive definite of CEP. So is CEP positive definite? I think some of you, if you actually audit the course some years ago, you know the answer. Okay, so let's take the previous example and let's take A equals to N. Okay, so N double dot CEP double dot N. I just want to know what is this equal to, right? Okay, because N I know is not equal to 0. Okay, you already know. So what happened to this term? Now I need to write it out. This term is actually equals to N double dot CE, now not CEP double dot N, minus 1 divided by x n double dot c e double dot n times n double dot c e double dot n. Okay, so what happened? So what is n? What is x? X is also n double dot c e double dot n. So n double dot c e double dot n divided by n double dot c e double dot n times n double dot c e double dot n is actually equals to n double dot c e double dot n. And so the first term here and the second term here actually cancel out, equal to 0. Okay, so what does that mean? Sorry, 0 is actually just a scalar. Okay, so what does that mean? So the consequence is that CEP is not positive definite for perfect plasticity. Okay. Now we just say that we don't want it to be not positive definite, and then now we find out that CE is not positive definite. So why is that? Okay. Now this is actually very important because I pick an A that very special. This is N. This is the flow direction itself. Okay. So why is it not positive definite? What is the physical implications of CE not being positive definite? It's actually in the analog of the 1D case of perfect plasticity. In the 1D case where I have perfect plasticity, I will have the loading and then I will go in this direction. This would be exactly x equal to 0, no hardening modulus. Okay, because my yield stress in 1D is not going to change. So I would have that in 1D, I have the yield stress that are actually forever equal to a constant, equals to Kuiper, and that is not going to change. Okay, so what happened to the strength stress relationships? Okay, it's not 1-to-1, right? Isn't it? It's clearly not 1-to-1. Why is that? It's actually many to 1, because I can have a strength here, I will lead to this stress. I can have another strength here, I will also lead to that stress. Okay? So what it means is that if I know the strength, it won't be sufficient for me to know what is the stress. Does that make sense? If stress and strain are 1-to-1, I should be able to knowing one and then map it to the other one. Okay? Because the inverse exists. Okay? But here there is no inverse. That doesn't make sense to have inverse. If I have a curve that looks like this, okay, I can view this as x and this as y, but if I look at y and figure out what is x, I can actually still able to find, if I know x, I can know y, or I can know y, I can know x. Okay, I just map it in a different way because the inverse exists. Here the inverse doesn't exist for a very simple reason. In this particular case, if you compute the eigenvalue of the elastoplastic tensor, it actually have a 0 eigenvalues. And that 0 eigenvalues, what is the corresponding eigenvector to it? Can you guess? It's just n, right? Okay, so why is that? Can you see this? Why is this? So what is eigenvalue for matrix? Okay, you compute eigenvalue by A minus lambda I determine equal to 0. Okay, you see what I mean? You try to using it. Okay, what is your eigenvalue equal to 0? What do you get? This thing equal to 0, right? And then you get determinant of A equal to 0, isn't it? Okay, so here this is not positive definite, and in fact you will find that is singular. Okay, and that singular is corresponding to the n directions. Okay, so this is actually why perfect plasticity model, you can put it into the material, you can put it into the eigenvalue in the computer. Okay, you won't actually get the perfect plasticity. Why is that? because the computer doesn't really store the zero unless you model it as an integer. You will have some floating number, you will have some tolerance, and then it will flip-flop, but it doesn't matter. So it would usually lead to the CEP that are not stable. So when it's not stable, what it means is that you can actually have zero energy mode related to the plasticity. So you can get those shear weird shape like a shear bang, and one of the reasons is that CEP is not positive definite. Okay, you can also have some other pattern that manifests from that you won't see it from the elasticity. Okay, so I go over this theoretical part, and now I want to finish this with the algorithm. Okay, so now we go over the theory in great details. Now I need to think about how to put it into the algorithm. Notice that the algorithm share by whether you do a machine learning part, a use service, or actually the handcraft. You still have to handcraft this return mapping algorithm. Okay, so are you ready? So, well, regardless, let me start. Okay. Okay, so we call that sigma is actually equals to the volumetric part plus the territory part. Okay. Now for the meso stress, I actually can put it in the principal stress space. Okay, and I have a hydrostatic axis pi that are increasing, and then I will have the actual shear. And then geometrically, what I have in the piping is that I will have the total stress, and then the stress that is normal to it is actually the territoric stress. Okay, why is that? Why do I write a 90-degree here? Okay, if you recall from the last lecture, pi double dot s is actually equal to 0. Okay, so a dot product equal to 0, or as actually a scalar product equal to 0 in the sense of the tensor, tell me that the two physical quality are orthogonal to each other. Okay, so here it manifests as a 90-degree angle that we can see here. Now if you're actually looking at it, if I put my eyes exactly here, I don't know have that much eyeballs, but anyway, so then we have the piping that actually look like this, and this sigma 3, sigma 2, sigma 1, and then I would actually have the S that stay here, and then the P would be here, and then that P is actually shooting outside in this iPad. Okay, does that make sense? Okay, so this is our original this, and then there's a line here. Okay, this is a hydrostatic ping. Okay, so my iPad pen is a hydrostatic ping. Now I try to look at it like this. Okay, that give me the piping. Okay, you understand that? Now this line P sigma 1 equal to sigma 2 equal to sigma 3 is pointing directly into my face. So that line vanished and become a dot here. Okay, you understand that? Okay, can you see that? It's actually we talked about it previously. Okay, in that space, in order to describe the circle, I reduce the dimensions from 3 to 2. In order to describe the circle, I only need any positions in that circle. I only need the radius and then the angle, right? Isn't it? And then the radius is constant, so I only need the angle. Okay, so, and then the U criteria is F equals to S minus K, and that if it's yielding is equal to 0. Okay, so let me talk about some old school stuff. Okay, so the first one to attempt to numerically program that return mapping is actually, according to the best of my knowledge, is Riken. '64. Okay, what he actually proposed is something called a radial return mapping, or return mapping algorithm. Okay, what does it do? Okay, so I will just list all the ingredient there again. Okay, the partitions of the elastic and plastic part, and then the stress increment only related to the elastic part, the plastic flow directions, where n is actually nothing other than the direction part, the normalized part versions of the territorial stress. And then I have the perfect plasticity, so Kuiper is actually equal to constant, meaning that the U surface is pinned down there on the piping and never move. Now I actually need to start to introduce the increment. Okay, so for a given time step, let's say I want to marching from, so march from Tn to Tn plus 1. Let's consider two incidents. And then the information at Tn is given. And then the only thing I know about between Tn and Tn plus 1 is the change of the elastic strain. Now I write the total stress, stress is actually equal to the tri-stress minus the correction term. Okay, do you all get this part? Okay, the tri-stress is actually where the tri-stress is actually equal to the previous stress plus CE double dot at delta epsilon, where I'm assuming that the previous time step before the previous step and the current time step, everything is elastic, which of course may not be correct, so I have this correction term. I understand what happened to the video problem right now, because when people call me, I think that this lead to a stop in the recording. So I try to see what I can do with the missing voice. Okay, now but then the problem is the following. I don't know what is this. Okay, so I actually need to find a way to expressing this properly, and then the change of the plastic strain require us to do one thing, which is actually to do a time integrations between Tn plus 1 and Tn for the change of the plastic strain. Okay, so this is the integral in time. Okay, so why is this equation correct? Okay, so lambda dot n is simply epsilon dot p, right? So this whole thing is actually epsilon dot p. Okay, so if I actually know the time, if I integrate in time, I should be able to get the change between the two time step. Okay, does that make sense? Now here in practice, I cannot actually do that because I don't know how does the n change and the lambda dot change analytically, but I can actually assume I can take a penalty of making it less accurate, but write a simpler expressions. I can assuming that is actually equals to delta lambda times n plus 1. Okay, so between time tn and time tn plus 1 is changing. Okay, can you see that? It can change, or it may not change, but it could change. Okay, but I'm actually assuming that I'll just take the whole thing. I'll just take the n plus 1. I'm assuming that it doesn't change, and then I would actually accept there's an error. And this is actually called backward difference. Okay, you generate a first order of error but instead we have a easier expressions. You can also do forward difference, but a forward difference may give you a conditionally stable return mapping algorithm, and that won't recommend. Now this would actually lead to delta lambda times Sn plus 1 divided by the norm of Sn plus 1. Okay, in that entire derivations, all the physical quality are actually discretized in time steps. So the n plus 1, the subscript, is actually representing what the slope in the time. Okay? So far so good? Now I'm going to put it back into these portions, which is really where I want to get the expressions. Now I have this equal to this. So what I have is that CE double dot delta epsilon P is actually equals to K I times identity tensor product of the identity tensor minus the 2 new I minus 1/3 of the identity matrix. So identity matrix. Okay, and double dot delta lambda and n plus 1. Now this is actually product coming from the backward difference. Okay, so far so good. Now the next question is more interesting. What do we have from that derivations? Whether you can see the pattern depends on whether you listen to me in the last lecture, which I assume that not that many people actually listen to me, but I hope I'm wrong. Okay, you can come up with very simple expressions. Again, the hints is on the orthogonal behavior between the volumetric and derivative term. Okay, do you know what I'm talking about? So the first thing I need to consider is what happened to this double dot this. Okay, what is the result of this? Yeah, what is this? Zero. Why is that?
Because the first term is volumetric and double dotted with the deviatory part, so that gives us zero.
Yeah, okay. If you work it out, you'll find out it's zero. That's correct. Okay, that's very good. How about the second term?
Two delta lambda times n plus 1.
Okay. That's absolutely correct. So this term, we just take out the fourth order tensor product by definitions, and then I will just have this. Okay, is that magic, right? Okay, so which makes sense. Whatever bulk modular you have, it doesn't really matter. Okay, because your Pasik deformation is only depends on the derivatory part. Okay, so anything that are coming from the bulk modulus are taking out because the elasticity is isotropic also. There's no coupling. Okay, so shear and volume are completely separate in the isotropic elasticity part. Okay, so what does it indicate is that now if I substitute this result back into my elastic update, the stress update, I would actually have the new stress equal to the child stress, which can assume everything is elastic, minus 2 lambda, so 2 times the shear modulus times the delta lambda times n plus 1. Okay. Now let's do the following. Let's double check by taking the diagonal term and sum it up together, shall we? Okay, take a chase to it. Okay, So if I actually apply the chase operator, okay, what do I get? So chase of the sigma n plus 1, okay, is actually equals to the chase of the drive stress. That's it. Okay, why is that? What is the chase of n? 0. Okay, there's nothing. Okay, so this is interesting. So Pn plus 1 is actually equals to Pn plus 1, the child state. Okay, which is makes sense because I know that all the plastic deformation is coming from the shear anyway. So of course, the volumetric part, I can separately compute the stress update already because all the volumetric deformation are supposed to be elastic. Does that make sense? Okay, so I also have an easier problem. I forget about what happened in the volumetric part. I only care about the diatoric part. Okay, I only need to measure how much diatoric plastic deformation I have, in particular because I don't have any volumetric plastic deformations. Okay, does that make sense? Okay, so this is just some coming from the physics. Now, how about the diatoric? Okay, there's one very important thing that we can come up with that derivation, which is the following. Because the volumetric part is taken out, so if I actually going back, substitute it to these equations, what I will have is the diatoric versions Sn plus 1 equals to the Sn plus 1 chase minus 2 nu delta lambda sigma n plus 1 divided by sigma n plus 1. Okay, this is just the substitutions. Now there's one thing that many of us doesn't notice but are very important. I have the Fn Sn plus 1, I have the Ns plus 1 chase, I have the Ns plus 1 here, and then I have the magnitude. Okay, so far so good. Now let me write rearranging my term here. Then what I will have is that is 1 plus 2 nu delta lambda divided by Sn plus 1 times Sn plus 1 equal to Sn plus 1 chase. Okay, do you guys see anything interesting here? Do you see anything interesting here? Actually, there's something very interesting to that in the sense that if I actually, again, taking actually times everything by the norm of the matrix norm of the S n plus 1 chase, and then what I will have is the following. N plus 1 is actually equals to the Sn plus 1 divided by the S norm n plus 1. But the second expression is way more important. Sn plus 1 chase, the child state, is actually equal to S plus Sn plus 1 chase. Okay, this relationship is actually very important. Okay, why is that important? Because of the TR thing. Okay, because what I'm actually telling you is that the direction of it is already fixed since the very beginning. I only need to correct lambda. Okay, does that make sense? Okay, because if I have a U surface at a circle, and then I already know this is actually the n directions, it doesn't really matter. I'm actually have a charge state that are outside of the U surface. I only need to go back to here, okay, with the right amount of the correction term, okay, coming from that 2 nu delta lambda, and I can go back to the U surface perfectly. Okay, the direction never changed. I just overshoot in the same directions. I just correct it back into the same direction, and then I will onto the U surface. Okay, what I did not do is that I did not go here or here. Okay, because that would imply the change of the directions between the child stress and the actual stress, right? The directorial part of that never changed. Okay, I'm just changing the magnitude so that I know initially I'm actually overshooting, and then I'm using that directions as a template. I only correct it with adjusting the magnitude so that I can hit back into the U surface. Okay, so this is actually a very important trick to actually make the prediction much easier, because then I don't actually need to predict n. Does that make sense? The entire return mapping algorithm only predict one thing. I only need to solve one thing. And what is that one thing? Delta lambda, okay? And delta lambda is a scalar, okay? So if I can update delta lambda, the whole thing is updated, okay? Does that make sense? Okay, so eventually, I don't need to something very simple. I just need to check the consistency here. Consistency requires that if f at n state is actually equal to 0, then f in n plus 1 is actually also equal to 0. Does that make sense? Okay, now I'm doing it in incremental form. Now what we actually require is that if I write out the expressions, then what I would have is that s n plus 1 minus Kuiper need to remain 0, right? Does that make sense? Okay, I still on the U surface, okay? And then what I would have is that sigma n plus 1, Sn plus 1 equals to Kuiper. Sorry, Sn plus 1, the norm of the Sn plus 1 is actually equal to Kuiper. Now, if I actually write out Sn plus 1, now then there are two terms. One is the magnitude, which is actually the norm of it. Another one is the directions. So I can write the derivative stress in exactly this way. Okay, does that make sense? So this is actually give me the two index, n give me the two index, and Kuiper is a scalar, give me the magnitude. And this, on the other hand, because n is also equal to the chase stress of the child stress of the derivative portion of the child stress, so I have this. Okay, does that make sense? Now, if we look at it, okay, if I actually consider this as a, which is actually the original radius, then I will have k divided by a times Sn plus 1. So, and what I would have is that the child stress, tri-derivative stress, and the true derivative stress, they are actually proportional to each other, and that proportion ratio is Kuiper divided by a. Okay, and a is the magnitude of the child stress. Does that make sense? Okay, so what you have is the following in the piping. If you look at it and then imagine there's a cartoon to show what happened, I would have a circle here, and then I would actually have some stress that are actually sigma n. It could be elastic or plastic. And then in the next step, I have stress n plus 1 child. And then the derivative part would be into this. And then I just need to correcting this term, and then I will add back the sigma n plus 1. Okay, you see what I mean? So, and that would actually give me back the corrections, and then so that I would have sigma. Once I update the sigma Sn plus 1, then I can actually update the entire stress, because again, the Pn plus 1 is equal to the P child n plus 1, and then I would simply have this. Okay, so the entire philosophy, I want you to not only follow the derivation, but understand the underlying philosophy of writing the J2 is very simple. Okay, it's basically following a divide and conquer strategy. I basically initially have a second order tensor calculus thing, very clumsy, very complicated, but I keep leveraging the orthogonal between the directoric and volumetric stress, and I keep using this as the basis to keep simplifying the problem, and eventually we need to algorithm that only need to update a scalar, and we already know the exact solution of the scalar. Now this problem is actually backward implicit, okay, because of the time integration term that I use. I'm assuming that and then this is actually, as a result, only first order accurate because of the error generated from the backward differences. And the important thing is that it's also exact for the radial direction for radial loading. Okay, you don't lose any informations if you're actually loading it in the radial directions of the stress. You only actually get some error in all the other directions. Okay, so I actually running out of time, so I think it's a bad idea to go through this first, because I think that you need to know how to hand graphing this by hand before you can actually know how to put the machine learning there. So human need to learn first, and you know what's going on before you know how to use the machines to actually. Otherwise, you cannot control the machines. Do you understand what I'm saying? In fact, now I talk about that, I'm also thinking about whether I should talk about Camcray or Zuckerberg or some more complex material model. Okay, so I think that what I can do is that I will prepare the J2 real-time mapping algorithm. So like exactly what we talk about, you can look at it yourself, and then take some time to take a look, and then we will have a discussions next week. And another thing is that I try to schedule time to talk to every one of you, and then about the final project. We haven't talked about the machine learning thing, but I